Rules and general concepts. In this chapter, we'll talk about some of the most important rules written in this standard. Dimensioning and tolerancing shall be complete so there is full understanding of the characteristics of each feature. So no missing dimensions are allowed, no suppositions, no estimating by drawing proportions, everything must be clear. 90 degrees angle applies when center lines and lines depicting features are shown on a drawing are right angles and no angle is specified. That's why we don't specify angles between horizontal and vertical lines. Unless otherwise specified, all dimensions are applicable at 20 degrees Celsius or 68 degrees Fahrenheit. Remember that materials expand when heated. That's why it is important to define a standard temperature. That's why metrology labs have a well-controlled temperature. All dimensions and tolerances apply in a free state condition. This principle does not apply to non-rigid parts, so the parts can be deformed to make it comply with dimensions. Dimensions and tolerances apply only at the drawing level where they are specified. You can specify dimensions for a part in different drawings. All the information should be present in the current drawing. Let's continue looking at more rules. Each necessary dimension of an end product shall be shown. Here, we can see that we're missing some dimensions to define this part. It's very basic, but it's actually helpful to know it's stipulated in the standard rules, so you can always demand the full definition of the part in a drawing. Here are the dimensions that we're missing of 10 and 8. Dimensioning and tolerancing shall clearly define engineering intent. No more dimensions than those necessary for complete definitions shall be given. Here we have the opposite case. Now we see repeated dimensions in the views, which can create conflicts. For example, we can see that we have specified individual length. However, by placing also the total length dimension, we overdefine the drawing, since it is possible to meet the individual dimension tolerances and do not comply with the total length of 27 within tolerance. Also notice that some dimensions such as 8 and 10 are in both views, causing confusion. That's why only the necessary dimensions should be placed. We see in the same part drawing, but now to avoid overdimensioning, we've set the repeated dimensions as reference by placing a parenthesis on them. Even though putting too many dimensions causes confusion and sometimes reference dimensions are taken as official dimensions, therefore the use of reference dimensions should be minimized. Each and every one of the dimensions in a drawing shall have a tolerance specified. It is impossible to make perfect parts. It should be always specified whether a dimension is critical or not, if it's allowed much or little variation. The exception to this rule is in commercial stock sizes. For example, if a half-inch screw is specified, tolerance is not specified on the drawing, as it is already specified on the thread sizes and standard. Or for example, when indicating a 16 gauge steel sheet, which follows a different standard. Now we'll see the importance of the location of dimensions in our drawing. Please calculate which is the maximum value that can be at the distance x. Pause the video and resume when you have the answer. Ready? A simple way to do this is to separate the dimensions from its tolerance. Then sum the dimensions and tolerances separately. At the end, add both amounts, and in this case the result is 27.6. Now let's calculate the maximum value that the distance x can be. Note that the tolerances for all the dimensions haven't changed. There's still 0.2, but now the result is 27.4. For the last time, calculate distance x. Now we can see that the dimension is directly indicated, so in this case the maximum distance of x is 27.2. In the last three examples, we have seen how the total length varies by changing the location of dimensions, even though these had the same tolerance of 0.2 in the three examples. The dimensions must be chosen and located to meet the function and assembly with adjacent components, and should not be subject to more than one interpretation. In the first case, the individual dimension is the most important. In the third case, each dimension is more important in relation to the base. We have seen how by changing the location of the dimensions changes the tolerance stack, also known as stack-ups. Now, let's see a couple things that differentiate a drawing dimensioned on inches from millimeters. When a drawing is expressed in millimeters, if the distance is less than 1 millimeter, a 0 is placed before the decimal point, and when it is an integer, neither 0 nor the decimal point is displayed. Here we can see the two examples. At the top, dimensions are specified in inches, and at the bottom in millimeters. In this case, we can notice because dimensions smaller than 1 have a 0 before the decimal point, in the case of millimeters. Please identify each group of dimensions, either if they're expressed in millimeters or inches. Find the zeros before the decimal point or integer dimensions without decimal point. Pause the video and resume when you have the answer. Are you ready? Here are the results. The group of left is noticed in millimeters. Notice the 12 doesn't have a 0 after the decimal place, and the 0.9 shows a 0 point before the decimal place. While on the right side we have inches. We can see all these dimensions that are less than 1 and don't have a 0 before the decimal point. ASME Y14.5 standard contains fundamental rules to standardize engineering drawings, is not limited only to geometric controls.